I just wanted to switch gears a bit, and because we don't just do proteomic software, we also do some metabolomic software. And we put out this paper earlier in the year that we're really happy with, and I just wanted to show you some of the work that we've been doing here because I think it's really interesting and opens up some new ideas potentially for thinking about how to analyze proteomic data as well. But really, I think if you look through the metabolomic literature, you'll find that oftentimes people will overreport pretty frequently in the number of things that they detect. So it's not uncommon for someone to show you a list of 10,000 features or 20,000 features and say, I found all of these features and they're all changing. It's really hard to take that list of maybe 1,000 changing features and figure out what that actually means. Actually, how many metabolites does that belong to? So it's not really that you've detected 20,000 or 30,000 metabolites. There really aren't, in a lot of these fluids, there aren't that many metabolites to even find, right? The real issue, I think, is hammered home in this paper in Gary Patty's lab. And this is quite recent, right? This is 2017 that he did this publication. So this is like an issue that we were facing 15 years ago in proteomics is really trying to be dealt with now in metabolomic space. But he was demonstrating in this paper a list of over 25,000 features that were detected out of a single E. coli lysate that were caused by different metabolites in that lysate. And then after you started to break down where those features could actually come from, they could be different adducts, they could be different in-source fragments, they could just be different weird isotopes that you weren't expecting to see. There could be contaminants of a variety of different ways. They were able to break this down into less than 1,000 actual metabolite features that they could actually discern and pick apart. And then at that point, they could start to think about identifying them. But if you started with this giant list of 25,000 features, it's impossible to be able to say, what's actually changing in these samples. So you guys all know this, but I just wanted to walk through this workflow. Typically we're taking metabolites and running them on an HPLC, separating them out and putting them into the mass spectrometer and collecting, an MS1 profile and a bunch of MS2 spectra. I think one of the things that oftentimes we forget is that we're putting a lot of energy right here when we're charging these metabolites. And what happens when they actually enter into the mass spectrometer is that they start to break apart and fall apart. So this was a paper out of Gary Sustak's lab last year, where he was analyzing where do in-source fragments come from. And he noted that over 90% of metabolites actually showed some signature for an in-source fragment, which is kind of disgruntling because already that means that we're going to double our potential false positive rate because there's going to be another n number of metabolites that are going to produce fragments that are going to be detected as other metabolites, right? Because they'll have a different precursor mass. So there's only 8% of the plus. I guess this is in the positive mode metabolites actually show no in-source fragments whatsoever of any kind. So where do these in-source fragments come from? A lot of them come from obvious neutral losses, loss of water, loss of ammonia, just like how we're used to seeing in DDA data for peptides. But we also see adducts, a lot of adducts in these samples. A lot of them are contaminated with some sort of salt, sodium or potassium. Some of them could be dimers or trimers even, or can glom together in other different arrangements. And a significant fraction of them actually share a lot of the same fragmentation as you get with CID fragments too, right? As if you were putting them into a collision cell and actually breaking them apart with higher energy. So let me just show you what some of this data looks like. So I've got this figure here. I've got retention time in this axis, M over Z, precursor M over Z in this axis. So this feature right here is also co-eluting with another feature right here. And if I look in mass bank, this one assigned very cleanly to methionine. So this peak right here is methionine, and this peak right here is an in-source fragment that is basically from the library. But if you see around this peak, there's a ton of really highly abundant features, and this is just in a very small MZ space. So this precursor was never selected for DDA, right here. So we were never able to actually collect an MS2 for this one. But we actually have an MS2 signature for this peptide just in the MS1 space. Does that make sense? So we started to see data like this, and we're wondering how could we actually leverage this? How could we make potentially detections out of the MS1 data as if it were MS2 data? And so these in-source fragments actually provide a lot of different complications for interpreting the data. So first one is, if you have to start searching with adducts, so if you start having to search with sodium adducts or potassium adducts or ammonia or something like that, every one of those will increase the search space. So it's as if you're searching for PTMs in the proteomic search space. Every PTM, every extra PTM you search for, the worse your overall search results are because your search space is that much larger. And so your false discovery correction needs to be more aggressive to be able to balance out the extra potential metabolites you could be finding. Also, the in-source fragments, because their precursor mass is different, they typically get assigned to other things, right? So they might get assigned to that 133 fragment has a precursor signature and will get assigned to something else in the library that's 133. And that really is a false positive because that was belonging to the metabolite, the methionine metabolite. But the idea here is that there's a potential for a lot of opportunity if we start to be able to acknowledge that we see these co-eluting in-source fragments and adducts that are coming out at exactly the same time. They just have different precursor masses. We can potentially notice them in retention time space, pull them out of the data set, and then use that information actually as a pseudo MS2 to be able to detect those metabolites. So we built this algorithm to do this that's been put into Elements that we're pretty excited about because I think it's changed how confident we are in our metabolomic data. The idea here is that we would see co-eluting fragment ions or co-eluting ions that are in the precursor space. So this is just MS1 space. We see that they have the same peak shape, and then we'll group them into a peak group. We'll take those peak groups across a bunch of different samples. So we'll have a sample 1 and a sample 2, and we'll see that these samples have, in these different peak groups, very similar ions at about the same retention time. We'll group those together to give us more confidence across multiple samples what all the potential co-eluting fragment ions might be. And then from that consensus across all of the different samples or acquisitions, we'll try to do a detection step and try to say, how good is my isotopic distribution, how well does it match the fragment ions in my library spectrum, and then cluster those into different groups, so based on the amount of evidence for different detections. So for example, if I have 5 co-eluting ions, and 3 of them clearly belong to one metabolite, but 2 of them don't make sense in our analysis, we'll take those 2 and then we'll go and relook for them as a potential secondary metabolite at the same time. Does that make sense? So to kind of benchmark this with Elements, we ended up using this data set that contained 75 known metabolites injected into a yeast sample. And then analyze them, benchmark them against a bunch of other approaches in the wild using XCMS, and found that Elements was doing just better in general in terms of being able to pick up peak features. So we were able to find 73 of the 75 known standards, searching them against the Metlin and the NIST databases. These are databases that are included in Elements by default. So of those 75 metabolites that we knew were actually present, if we look and see which of those we're actually being able to detect at the MS1 level, we note that, of the ones that we can say actually are in the highest scoring group, or highest score, that basically get a good score for that metabolite in that sample. We can typically find a peak feature that matches up to what we were expecting in our search space at like this 97 or 98%. But if we want to be confident that this is definitely the metabolite that we're interested in, we have this unambiguous and unmistakable score, which basically says, was this metabolite actually detected uniquely assigned to all of these different fragment ions? Can we definitely say it was this metabolite and not some other metabolite that might have also been a possibility? What we find is that using these in-source fragments, we typically end up getting a lot more detections as a result. We're much more confident in the results that we see out of this MS1 analysis. But if we actually start using MS2 data, we actually find out that it does pretty much the same thing. So for this MS2 data, if we include the MS2s as part of our detection rates, again, we can see an increase after using the in-source fragments. So the addition of seeing these in-source fragments, even if we've collected MS2s, improves our detection rate. But I think one of the things that was sort of shocking to us that was brought up after a reviewer comment was that actually, if you look at some of these metrics, for the unmistakable and roughly for here, the in-source fragments do really well relative to the MS2s. And this was a little bit shocking to us, that basically if we were looking at MS1 only data, which frankly a lot of a big subset of the metabolomics community is still collecting MS1 only data and analyzing MS1 only data, we actually can be fairly confident with that data and use these spectrum libraries to be able to identify metabolites out of it, as if you were collecting MS2 data, in a sense. So this was kind of exciting to us, the ability to say we're able to do as well or potentially even better in some circumstances if you don't collect MS2s and just analyze the MS1 data. We're more confident in the results. So that was a little shocking to us. But there are actually a lot of reasons why that might be. In this particular data set, this was done with an LTQ orbit trap. So the precursors were collected in high-res mode. The fragment ions were collected in the ion trap, as is typical for proteomics experiments as well as metabolomic experiments. And the addition of the high mass accuracy gives you, because basically this gives us a chance to analyze high mass accuracy fragment ions, as opposed to just the precursors in the MS1 space. So now we're getting high-res fragment ions and comparing that against low-res fragment ions with the MS2s that we collect. The other advantage is because we've got consecutive scans, 6, 8 scans right in a row, we actually are more confident about the precursor mass, and we're more confident that that ion is actually present. So when you think about the noise that you see in an MS2, we're actually removing a lot of the noise that's due to just electrical signal or due to some unusual contaminant that's coming into the mass spectrometer at that time that doesn't time repeat from scan to scan. We actually can cut a lot of those ions and be able to work off of only the ions that are actually co-eluting with the fragment or with the precursor. Another big advantage is that typically with the MS2s, you're not usually collecting them at the apex of the peak, right? You're usually collecting at the early shoulder because it's the precursor signal rises to a certain level, you collect the MS2, and then you stick it on an exclusion list. So we don't actually see it when it's at its best. But here with the fragments, we actually see it when it's at its apex, at its top point. So just to give you an example here, this is a UDP glucose signature. This is just the precursor signature here. And we see a bunch of these co-eluting fragment ions that are just in the MS1 space, not even looking at the MS2s. And we can see that they all line up at the same time point, and we link those those different ions together, and then basically do a lookup in these spectrum libraries as if we had collected an MS2 with this synthetic MS2. And we get stuff that actually relates back to the structure to say that these fragment ions make sense respective to what we're expecting to see for this metabolite. So all of these ions in yellow here are ones that we identified out of the precursor signal, and then these are the ones in the library. So we're basically doing a library search, but without even needing to collect the MS2s. So this is kind of an exciting avenue for us, actually, because not only are we seeing that, we're getting better results in some cases than if you collected MS2s, but even if you collected MS2s, we can use our additional information to augment the MS2 level data too, right? So you can use the MS2 peaks and the MS1 peak group and line those two together and say, yes, we are confident that this is the right set of ions to be looking for. It also removes a lot of the false positives, frankly, that are caused by these co-eluting adducts or co-eluting in-source fragments. And so as a result, we're feeling like our detection rates are actually going up substantially from this. One of the things that's been sort of shocking to us is that this might actually breathe new light into these MS1 only data sets. So if you happen to have an exactive sitting around, for example, without the quadrupole, just an exactive, you could potentially collect really high quality MS1 only data at high res and potentially be able to make those detections for about half the price of a Q-exactive instrument. We are pretty excited about this approach. And so if you're doing metabolomics, we think that you should be interested and want to try it out. Tony?
Have you tried to change some of the voltages in the source to actually increase your in-source fragmentation?
Yeah, potentially if you were running something that was like an exactive only, and you had no chance other than looking at in-source fragments, I think it would make sense to increase the voltage on the source. Here, this is done without any voltage. So without any, not without any voltage, but without any like in-source fragment, because there's a setting that you can do to increase the energy in the source. Yeah. So this is done without any of those crutches, but potentially you could use that to do even better, or be able to see these even more. Cool. So that's what we wanted to say about elements. Again, this is new stuff this year that we've been pretty excited about. The idea that we can start to think about using this strategy for proteomics is also something that we're pretty excited about too, because we do see a lot of these in-source fragments as well in proteomic data, and those get database searched just like everything else, right? So I think that's one of the advantages that or these hidden advantages that we see with DIA, where you're not as beholden to these in-source fragments. That said, a lot of them...
The one that's really typical, and if you ever look at it, but the 842 or 421, you have trypsin peak. And if you look at that actual spectrum, you will see a lot of sequence fragments. And a lot of the older instruments, I haven't looked at the newest, but when I had an LPQ, for example, the auto-tune would end up giving you settings that you had huge amounts of those fragments. And I would change the settings a little bit so that we didn't get so much.
Mm-hmm.
And but I always wondered, because what you end up with is a lot of extra. And if you search with a no enzyme specification, you often can get that assigned piece. But
yeah, so you can definitely see a lot of these. I think this is pretty exciting for us, though. I think it's cleaned up the data to a degree that we feel like this metabolomics data actually is pretty good.
Well, see, there's a problem with metabolomics, because I've also used that and run in my lab, having done small molecules first. And in proteomics, we're very lazy, easy. You can use 30% collision energy, 35, 32, whatever. But here, the small molecules have a very specific range. And sometimes if you use a step collision energy, that will help. But you may not have the ideal settings, and you may have too much energy for your molecule in your actual collision. And so you're getting a much more gentle fragmentation in the source. And it is complementary information, not overlapping. I mean, not identical.
Yeah.